Hello everyone! Welcome back to Be Talking About Brains. And also, welcome to my newly organized bookshelf. If you've seen a previous video of mine, a vlog, Alex organized my bookshelf. Look at how pretty it is. I mean, you actually don't see the lower part, which is also wonderfully pretty, but like my makeup is organized and my books are organized. It's great. Thanks, Alex. So, today's finally, after half a year, I told you this is not going to be following any schedule. After half a year, the second video for my little thesis series is finally coming. Finally made myself sit down and write a script for neuroimaging. More specifically, the neuroimaging methods that I looked at in my thesis that were used in the studies that I employed in my thesis. So, obviously, since my thesis focused on structural characteristics, there's also just going to be a focus on structural imaging techniques. And so functional imaging and neurochemical imaging will be ignored in this video. There are tons of other techniques out there. I'm just going to tell you about two. First, some basics. There are two types of tissues that can be found in the brain. First one is gray matter, which consists primarily of cell bodies, dendrites, and unmyelinated axons. I don't know how I say that word. Unmyelinated. Not sure. Axons without a lipid mantle. We're just going to go with that. And then the second type of tissue is white matter. White matter is mainly composed of myelinated, or just myelinated axons with a lipid mantle. I really don't know how to say that word. I'm sorry, guys. So the term structural imaging refers to a collection of neuroanatomical data by magnetic resonance imaging, otherwise known as MRI. Probably a lot of people have already heard about MRI. It's pretty, you know about MRI. And the subsequent analysis of MRI data with regard to gray matter or white matter structure. So in this video, I'm going to describe to you the two types of MRI imaging, of structural imaging methods that I decided to look at in my thesis. First, let's look at T1 weighted imaging. I'll just be calling it T1 from now on. So T1 weighted imaging is one of the two major types of MRI images. I will spare you the physics details about, how all the atoms work and everything. But the basic processing of T1 weighted images includes the segmentation of gray matter and white matter volumetric structures and the modeling of local and global shape aspects of the brain. So, in short, you measure things like volume. You measure things like cortical thickness. You measure things like gyrification, which is cortical folding. Now, the statistical analysis of T1 data can either be performed on a whole brain level or on a region of interest level, or ROI level. For ROI analysis, you kind of have to define a area of interest, a region of interest first, which is then going to be the only thing that you look at. Now, this is positive in one sense because this approach is more sensitive to local differences. So for example, if you do compare participants, you compare different people's brains to each other, if you have an ROI approach, it will pick up on smaller differences than a whole brain approach would. However, there are also drawbacks, such as you have increased effort because you have to define those regions, so you have to have a certain degree of neuroanatomical understanding in the first place, and there is user bias. Furthermore, ROI analysis don't really answer the question whether the results are specific to that area of the brain or if same results could be found elsewhere in the brain, because outside of the ROI, you're not really looking at anything. Alternatively, we have VoxelBased Morphometry, which is a whole brain approach. It's kind of like, imagine you split the brain into tiny, tiny cubes, which is a voxel, like tiny cubes, voxels. And then you analyze the brain voxel by voxel. So after you've analyzed them voxel by voxel, you have to normalize this spatially, and you have to smooth the picture to get a somewhat even image. Now, since also the statistical comparison is performed voxel by voxel, you have a ton of statistical comparisons. Now, I can't really explain the entire statistics part here, because otherwise we have a math lecture. But the more comparisons you have, the more your probability for finding a false positive result rises. So the more comparisons you have, the more likely it is that you find something that isn't actually relevant, that isn't actually significantly different. Ultimately though, regardless of how you analyze T1 weighted imaging, it provides static anatomical information. As I mentioned before, you have measures such as cortical thickness, scarification or cortical folding, and surface area, and the most often used one, volume. Frequently used volumetric measures include volume quantifications of gray matter or white matter in defined regions, globally, like global volume by tissue type, intracranial volume, and total cerebral volume, which is the global volume of both white matter and gray matter. So, as you can see, we can analyze white matter with T1 weighted imaging. However, most studies using T1 focus on gray matter structure. Now, that being said, we're getting to our second type of imaging, which is diffusion tensor imaging, also known as DTI. And I'm going to be calling it DTI from now on. So, the investigation of white matter integrity is greatly facilitated by DTI. Again, I'll spare you the physics of it because honestly, while writing the thesis, that took a while. Like that. Whew, that was math heavy, a lot. And there is some math in the script that I might spare you. We'll see. So much like T1, DTI images can be analyzed for pre-selected ROIs or in a whole brain approach such as VoxelBased Morphometry. However, white matter structures tend to be much more homogeneous than gray matter areas. So voxel-based morphometry sensitivity is limited for white matter, which is why T1 weighted imaging usually doesn't really focus on white matter. Subtle differences could be lost by the smoothing process that is involved in voxel-based morphometry. There is an alternative though, namely tract-based spatial statistics, TBSS. Those were specifically designed for analyzing DTI data and eliminate the necessity for spatial smoothing and reduce the total number of tested voxels. Now, it's still voxel-based. So voxel-based analysis, including TBSS, they're designed to facilitate inter-subject comparisons by scaling individual images to a standard space. There is an alternative to that as well within DTI, which is tractography. Tractography aims at reconstructing 3D trajectories of white matter tracts. You can see it like tractography is the ROI type of DTI. So it has similar drawbacks to ROI analysis of T1, including that you need to have anatomical knowledge. You need to know which white matter tract you're going to be looking at. and you have user bias, and you have a complete lack of information regarding areas outside those predefined ROIs. Now, with T1, we can look at volume, we can look at cortical thickness. Those are all pretty straightforward measures. So what are we looking at? What kind of results are we getting from DTI images? Well, several measures can be acquired from DTI. Most frequently used is fractional anisotropy. And now it gets a little bit mathematical. Okay, great, we're back. We had to fix the hair, I'm sorry. Where was I? Fractional anisotropy can take values between 0, which is undirected or isotropic, and 1, which is directed, anisotropic. And it refers to the degree of diffusion restriction. Now, I mentioned earlier that the two types of tissue mainly differentiate between whether axons are coated with a lipid mantle, like a fat mantle. White matter is coated in such a lipid mantle, meaning that in white matter tracts, the diffusion of water is restricted. So in white matter fiber tracts in the brain, fractional anisotropy is highest because there everything is directed, it is anisotropic. Because white matter consists of myelinated axons. Not sure if I'm explaining this well, but just white matter, the water molecules in white matter tracts are very much going all in the same direction because they can't really diffuse through the fat mantle thing, which means high fractional anisotropy. So, therefore, high fractional anisotropy values are often interpreted as a sign for high white matter integrity, despite its dependence on other factors such as axonal density or potential pressure of fiber crossings in investigated areas. Like, all sorts of things can affect it actually, but it is most often interpreted as high fractional anisotropy means high white matter integrity, which is probably something that we would want, right? Yeah, okay, cool. Now we have some other DTI measures that are also used fairly frequently. Like, I've looked at some of them in my studies. Mean diffusivity is a measure for overall diffusivity within a voxel in any direction. So water can go in any direction, how much water is being diffused in any direction. Then we have radial diffusivity, which I'm actually not going to explain because it's kind of redundant. Axial diffusivity, and then we have tensor mode, which is, and I'm just gonna read that sentence from my script because frankly, when I wrote the thesis, I once for like 5 minutes was able to wrap my head around it truly understand what it means, and then it was gone again. So that's the sentence I have. Tensor mode is mathematically orthogonal to fractional anisotropy and therefore distinguishes the various modes of anisotropy, which is why it is also referred to as mode of anisotropy occasionally. We're going to call it tensor mode, and it's actually not that important. It only came up in 2 studies, whatever. It ranges from linear, where one fiber direction dominates, to planar, which means fibers with different directions are crossing. So basically, fractional anisotropy sometimes relies on or is affected by whether fibers are crossing in different directions, and tensor mode is a way of measuring whether they do or not. So that's neat. But we're not going to go further into that. What does it mean? The whole DTI measuring things, because honestly, volume and cortical thickness and surface area, that's pretty straightforward. Big brain volume, cool, great, that sounds really positive, wonderful. High fractional anisotropy, Could be anything, I don't know. Is it positive? Is it negative? Do we want it? Do we not want it? So the question of which biological properties are reflected by these parameters is difficult. It's like significantly more complex than for T1 measures, because those are really straightforward, in my opinion at least. I don't know if I'm just being pretentious because I familiarized myself a lot with this stuff when I wrote the thesis, but to me they're kind of self-explanatory for T1 with the volume and everything. So there are a lot of factors that affect DT1 measures, such as degrees of myelinization, degree of intravoxel fiber passage, and I'll just read that because terminology, axonal density, average axonal diameter. Those factors have an influence on fractional anisotropy, resulting in the pathological significance of fractional anisotropy reductions becoming rather difficult to interpret. Don't I write beautiful sentences in my scripts to then completely and utterly ignore them because I lack the editing skills to actually record every sentence. Like, I could record every sentence looking at the camera and just basically read my script. Do I have the patience to edit that? No, I do not. Which is why those videos are kind of improvised in the end. There you go. Maybe one day I'll ask one of my millions of editor friends to teach me. But not today. Anyway, so another relevant aspect in the interpretation of white matter anomalies is how those different DTI measures relate to each other. For example, if you have a dysmyelination of the nerve sheath that is associated with radial diffusivity, and axonal damage is associated with decreased axial diffusivity. Also, increased radial diffusivity and decreased axial diffusivity, or a combination of both, seem to be related or result in a reduction of fractional anisotropy. And honestly, those last 3 sentences or 4 sentences that I said, they're not that relevant for the rest of this series. I just put them in there honestly because maybe somebody's really interested in it. And if you are, hit me up. I can send you my thesis. There it's printed, much better than this weird explanation. DTI measures are really difficult to interpret. We don't have a clear, straightforward way to just say, okay, if axial diffusivity is high, that's good, and if that is low, then that's bad, and or like, it's not as straightforward as you want a thick cortex. That's pretty straightforward. Yeah, cortical thickness, good thing, cool. DTI measures, not so easy. So to sum up, before I just blabber myself into oblivion here, the 2 neuroimaging methods that I looked at in my thesis, or rather, like, I didn't do measures myself, the 2 imaging methods that I included, studies that I looked at, included either DTI measures or T1 data. Studies that use T1 reported measures such as volume, cortical thickness, surface area, and purification, while studies that use DTI reported measures such as fractional anisotropy, mean, radial, and axial diffusivity, and tensor mode, which represent white matter integrity. Now that you know about the basics of these methods, and really just the basics, if you want to, you can have a look at my thesis. If you want to, you can look at the sources in my thesis. Go ham. I'm really glad I don't have to do this anymore. We're all set for the fun part, because in the next video, I will be talking about the basics of ADHD, some fundamental ADHD theories that are influential nowadays, and honestly, maybe neuroanatomy. I'm not sure if I'm going to include the neuroanatomy in the next part because I started to write my script for the next video. I'm working on it, okay? I'm really trying to make those videos come faster. And I figured, like, I realized that the neuroanatomy, unless I want to give you a complete account of neuroanatomy, which is kind of not the goal, is probably better with the results, with the state of research that I just explained to you, what all those regions do while I report the results to you. So maybe that will be in a different video. So next video is about ADHD, and that's all I can promise. So I did start to write a script, but I still won't promise when that video will come. So I'll see ya whenever I motivate myself to do that. Bye!